In this video, we're talking about the remainder theorem. It's a very exciting and useful theorem in polynomial division and factorizing polynomials. So essentially what it says is if you divide a polynomial by x take k, you can know what the remainder is in advance without doing the division at all. All you need to do is sub in k to the original polynomial and you get it. So here's an example. We've got this polynomial here. And then if I want the remainder from this division that I'm going to do, all that I need to do is work out p of minus 3. Now be really careful about this. What you're subbing in is minus 3, and the way you know how to sub that in is minus 3 for the x value would give you 0 in that case. So the theorem says x take k, and you're subbing in positive k. So essentially you just need to flip the pluses and minuses around, kind of like when you're solving quadratics. Anyway, let's sub in minus 3 and see what we get. So p of minus 3 is going to be minus 3 to the power of 4 plus 2 lots of minus 3 squared, take 1. That is 81 plus 2 times 9, take 1. And if you work through this, you're going to get 98. Now, how do we know that I'm actually telling you the truth and this is the remainder? It just so happens that this is the division we did in the last video, and we got a lovely remainder of 98 there when we did it. So it sort of all checks out. It does actually work. The next thing I'm going to show you is a proof of the remainder theorem for a specific k value. Once this is done, I'd really encourage you to pause the video and try the real proof just for in general itself, so leaving k as k. But by almost definition, if our k value was 2, for example, a division looks like this. So you get a quotient plus whatever your remainder is over that same thing you were dividing by x take 2. Quite often what we'll do is we'll call, so in this case, the divisor is x take 2. So it's really that thing there that we're dividing by. And if you want a specific example with p's and q's filled in, we can actually look at the last bit from the last video there. So that's what it would look like here if you had p's and q's and r's filled in what they actually are in an example. All right, now that we've got that sorted, the next step that we're going to do is we're going to times both sides by x take 2. And that'll get us sort of to the other form that we like looking at these division things in. So times x take 2 to both sides. So this is sort of the standard way to write it, but there's another also standard way to write it. So it looks like this. Q of x times x take 2. And then we're just going to be plussing r, because if you think about timesing this by x take 2, then those two things will cancel off with each other. So that's where it all comes from. Now, really importantly, if I try and apply the remainder theorem here and sub in 2, that's our k value, what I'm going to get is q of 2 times 2 take 2 plus r. Now, we actually will not know what q of 2 is. We can't know that. But it doesn't even matter because this becomes q of 2 times 0 plus r, or in other words, that's just r. So that's a proof of the remainder theorem for k equals 2. I'd really encourage you to try just leaving this as k and see if you can prove it yourself in general. All right, we'll do an example question of what they like to ask with the remainder theorem. So this polynomial has some unknown, it's a, but they have given us this information that when f of x is divided by that, the remainder is minus 5. So we can take all of this thing and put it into an equation. This tells us that p, or f in this case, of a half equals minus 5. Now, how did I know it was a half? It's because we're trying to solve this equation. So 2x would equal 1, therefore x equals a half. So this is our sort of k value from the remainder theorem. All right. Now, let's use that equation, and that should really help us find that a value. So f of a half equals minus 5, or maybe what I'll do is I'll put minus 5 over here. And then we're going to go minus 5 equals 2 lots of a half cubed plus a lots of a half squared. Take a half, take 6. That's going to give us 2 times an eighth plus a times a quarter take a half, take 6. So that's going to give us a quarter plus a quarter A, take a half, take 6. Now, we got a lot of nasty fractions here, and I want to show you just a general trick for dealing with equations like this. So we've got 4's on the bottom, we've got 2's on the bottom. If in theory I times by 4 to both sides, that's actually going to cause us to get rid of a lot of these fractions. So let's do that. Times by 4 on the left, you're going to get minus 20. Here, you're just going to get 1 plus A, take 2, take 12. Not 12, 6 times 4 is 24. So that's how that sort of all plays out, and it makes your equation a lot nicer to deal with. Probably next thing I'm going to do is combine like terms. So if we do that, you got 1 take 2, that's minus 1, and then minus 24. That's minus 25 plus A, and then the last thing to do is just to add 25 to both sides. So you're going to get 5 equals A. So it's probably not a bad idea to restate what the polynomial is here. So it was looking like this. 2x cubed, ax squared, take x, take 6. So therefore, f of x is 2x cubed, take 5x squared, take x, take 6. And I'll just make sure that I got that right. There's a plus there. That's good to know. Cool. All right. So that's our polynomial. One thing that you can do, it's not a bad idea to do this, is to actually have your polynomial graphed on a function. So I'm going to graph that polynomial that we just found. All right, then we can just graph that. It looks like this. So in theory, if I do sub in a half, I should get minus 5. So I can go trace and I can sub in a half and I get minus 5 for the y value. So that's good news. Now part B is asking us to find the remainder when f of x is divided by x plus 2. We'll just fix our window to make sure minus 2 is included. But in theory, what I should get when I do this is whatever the value is at minus 2. So I'm expecting to get 0 as the answer, which we'll keep an eye out for. So this remainder is going to equal f of minus 2, which equals 2 lots of minus 2 cubed plus 5 lots of minus 2 squared, take minus 2, take 6. And if we work this out, we're going to get, let's see, minus 16. This becomes plus 20 for that next term, because it's 5 times 4. 2 minuses make a plus, so plus 2 and take 6. So that's going to give us 22, take 22, or in other words, 0. So it's actually really important to know that, therefore, we can say that x plus 2 is a factor of f of x, because you know you get no remainder when you do that division. Hence, fully factorize f of x. So we'll just look at our f of x here, 2x cubed, 5x squared, take x, take 6. And then we're going to be dividing that out by x plus 2. So we know that x plus 2 is a factor. So if I divide it out, I'm expecting to get a nice clean division, so no remainder. So we'll give that a go. And it's our favorite thing to do, polynomial division. How many times does x go into 2x cubed? It goes in 2x squared times. We do 2x squared times all that. So I'm going to get 2x cubed plus 4x squared. Subtract those out. You're going to get x squared left over and take x. All right. How many times does x go into x squared? It goes in x times. So if we do that, then we get a times x by all the stuff up here. So we're going to get x squared plus 2x. And if we subtract those, you're going to get minus 3x. Pull down the minus 6. And again, how many times does x go into minus 3x? It goes in minus 3 times. We take the minus 3, we times it by all this. So we're going to get minus 3x take 6. And I've got a remainder of 0, which makes me very, very happy because that's what the remainder theorem predicted for this one here. So what have we learned? We've actually learned, therefore, f of x divided by x plus 2 equals this quadratic here, 2x squared plus x, take 3. And if we want to rewrite that, f of x equals, let's go with x plus 2 out the front, and 2x squared plus x, take 3. So we're on our way towards fully factorizing it. If you see something like this, and you're thinking about factorizing it, you could try and do like a sum and product or something along those lines. So let's see, first of all, whether or not that's actually going to work. So what I'd recommend you do is jump into polynomial solver here. We've got a degree 2, and we've got 2, 1, and minus 3 as our coefficients. We can solve that. So I know I am expecting some nice answers. So sum and product should work. In fact, the calculator just told us what we're going to get from sum and product. So the way that you deal with something like this is it's a little bit nasty because there's no, it's not 1 in front of x squared, it's 2 in front of x squared. So you've got to think about what 2x things would I times together to get 2x. And you're probably going to be timesing 2x and 1x to get that. There's only one possibility there, at least if you're looking at whole numbers. So then we sort of do our little crossy cross thing. And the numbers that we still put here still need to times to give minus 3. That's very important. So let's try putting some numbers. So if we try, let's say, minus 3 and 1, then basically what you do is you go down here. So that's going to give you 2x when you times along that one. And that's going to give you minus 3x when you times along that one. If you add those together, you're going to get minus x, which isn't good, doesn't work. So let's maybe try a different one. So 2x and x. Maybe we can swap these two. So we get 1 and minus 3. If we do that, so that gives you minus 5x. That does not match the thing in the middle, so no. What about if I tried having the negative sign on the 1? It could look like this, and 3. So we got 2x and 3, that gives us 6x, and we've got x and minus 1, that gives us minus x. Still doesn't work, but there's one more thing we haven't tried, putting the minus 1 down the bottom. So 2x and x. If we do that, you're going to get minus 2x, and you're going to get plus 3x. When you add these up, you're going to get x. And x was what I was looking for, because that was the thing in the middle. So if you do that, then you read off your brackets like this. That's a bracket and that's a bracket. 2x plus 3 and x take 1. The sum and product can be a little bit nasty when you don't have 1 in front of the x squared, but that's how you do it. All right, so we've actually answered the question. We've fully factorized f. And not that it's asking for it necessarily here, but we can actually say that the x-intercepts, these are going to be minus 2, minus 3 halves, and positive 1. And since we had our function graphed from before, if we go shift g solve root, then we can see, yeah, minus 2, minus 1.5, and 1. So that's good news for us. Now, this was an example of when there's just one unknown letter, A. I've actually got basically the same example, but I've left another letter unknown. Now, this one here, b is minus 1, if you follow the example above, because it's the same polynomial. But I really would encourage you to try as an exercise. Use these two pieces of information to get two simultaneous equations. And then you're hoping to solve for a equals 5 and b equals minus 1. So it's not a bad idea to try that if you want to try one of the harder style questions for this topic.